Okay, so let's start with a quick review of just informally just some of the things we've talked about the last few days. So we started with EMR. What is electromagnetic radiation?
Accelerating when it charges.
Well, that's what causes it. So, I mean, it's not a bad place to start. So, yeah, you have an accelerated charge. So, I mean, you're talking a proton, electron, alpha particle, I don't care what it is. Something that has a charge and we move it, you know, say from rest to moving, right? So that causes EMR, but what is EMR? Sure, that's an example of one of the types of EMR, right?
So all the different types of waves, like microwaves, gamma.
There's a word I wanted to hear. It's a wave. Right? EMR is a wave. That's probably the best way of starting it, right? It's actually also a particle, which is kind of confusing as well, because it kind of behaves as both. We'll talk more about that later. I don't want to get into the weirdness of physics too much yet, but I mean, it behaves as a wave, right? So hopefully you're familiar with that idea of if you have an accelerating particle of some sort of charge, right? If there is a moving charge, it should make a magnetic field. But if it is a changing magnetic field, it could make a changing electric field, which could remake a new changing magnetic field. And so one of the words that we use is like it propagates. You guys have heard that word before, where like one creates the other, which creates the next one and creates the next one. This should just keep going on for forever, right? So now coming back to one of you guys mentioned the idea of light. That's a good example of a wave. Light is one of the wavelengths of this wave. Someone want to grab that door? Thank you. Thank you. You're always one for it. Thank you so much for doing that. Okay, so I mean, in terms of this wave, one of the things we talked about in our last unit, like last Physics 20, right, is the idea of waves have they have amplitude, they have period, they have like a distance between crests. That's wavelength. So one of the things I need you guys to know is, I mean, approximately like how do these things fit into a spectrum? So the longest wavelengths we usually talk about are radio waves. Does that make sense? And then shorter than radio waves are, good, it's not on the board. Microwaves are next. After microwaves, infrared. And then visible light, which goes from red through to violet. After violet, ultraviolet. Then after ultraviolet, X-rays first. Then gamma rays, and then if we get that small cosmic radiation, but we don't really worry about that one probably. So I need you to know the spectrum. If you've seen the assignment, which I just finished making last night, I think a few of you printed it off. That's one of the questions I'm going to have for you is, make sure you know the spectrum. And I don't think you should memorize the wavelengths, but it wouldn't hurt just to have a rough idea of where they seem to fit. You know, in terms of like, is it a nanometer versus a meter versus a centimeter? So just know the rough size of all these waves, and hopefully you know some of the applications of what we use them for. Well, I mean, radio waves we use for radio signals, right? I guess, right? Microwaves, I mean, yes, cooking our food. Other things that operate on microwave frequencies would be like your cell phones. Those operate around that frequency in the spectrum, right? Light is stuff we see. Infrared, we can actually help like see in the dark. What about UV rays? What are they? There's like a big application of that. Say that again? Yeah, I mean, we need to try to block UV rays so you don't get sunburn, you know, cancer and stuff like that. X-rays, I mean, you're probably talking things like, you know, the dentist or, you know, a hospital, right, where you're trying to look inside of you to see your bones. You know, because some of these X-rays, I put this here, X-rays will pass through some materials, but they won't pass through other materials, right? So therefore, when they don't pass through bone, but they do pass through flesh, we can see the insides of people, right? But actually having to cut you open. Anybody know what gamma rays are usually from?
Isn't it like, from particles decaying?
Yes, that'd be one of the things you'd see them from the particle decay. I didn't phrase this very well. Nuclear explosions actually release gamma radiation as well.
So is that like from like radiation?
Yeah, like fallout. Right. Or nuclear fallout. So, anyways, that's the first thing we talked about. You should know the EMR spectrum. Okay. What we've been focusing on recently, then, over the last 3 days, then, is what are some of the things that this wave, EMR, whatever it is. I mean, we normally talk about light, but what are some of the things it can do? So, topic 2 was about reflection. It has the ability to bounce off of a surface and go somewhere else. Does that make sense? Yesterday's topic then was refraction. it has the ability to maybe go through a material, but as it goes through a more or less dense material, its angle is going to shift, depending on whether it's going from more dense to less dense or less dense to more dense. Does that make sense? So today's topic is probably the trickiest to understand. You guys probably have seen this before, you just didn't know the term. It's called diffraction. Okay? And we've discovered that light also has the ability to diffract. And so let me finally start looking at these notes here. It has to do about waves spreading out after going either through or around something. Let me show you a picture of diffraction from everyday life scenario here. So this is some sort of dam or bridge or something along those lines. And water is able to go through just this little narrow slit. And you've probably seen this before. What's happening here is water is now radiating out in a wave front that's kind of curved like this as it's coming out of this little slot. Does that make sense? This is diffraction. The ability to spread out after it goes either through or around an object. Would it make logical sense for this water to go through the dam and then just continue going in a straight line? And so you'd have like dry land just sitting right there and over here. Would that make logical sense with water? I think intuitively you'd say, well, no, isn't the water just going to spread out in all directions? Right? And waves basically have that same property. I mean, water can form waves, different kinds of waves, obviously, because this is more of like a physical wave as opposed to an electromagnetic wave. But this is diffraction. So, I mean, I have a bunch of pictures here that kind of illustrate the same concept here. Here we've got the same sort of thing like a dam, right? And what's happening is as these waves, as they hit the side here, some of them go through, but they're going to radiate out in all directions and eventually spread themselves out, depending on the size of this little hole in the middle here. Same thing if it goes around an object, though. So here you've got waves that are coming around here. These waves aren't just going to keep going right here and just you'll have nothing sitting over here. These waves will have the ability to bend and go around objects. And light actually does have this ability. We have talked about this briefly, way back when. I think I'm going to try to find that now. Give me a second here to find the Poisson bright spot, if I'm saying that right. Whoa, holy smokes, might have gone too far. Okay, I showed you guys this picture on the very first day, and I glossed over it because it wasn't really that relevant now, but let's talk about it today. This guy right here, Simeon Poisson, I'm guessing he's French, I'm butchering his name, I'm sure, actually, he thought that light should not be able to diffract around a disk. And so I think we talked about this story. Some other guy managed to find that it did, and so he named it after the first guy, kind of making fun of him in a way, saying, haha, you were wrong. So here's a good picture, hopefully, of it. If light were a wave, and it's going to go like this, and there's like a big object here in the middle. And then same thing, light is going to go in all directions. It would even go this way, and it would go this way. If it went right here, it would just hit the screen, obviously, and you'd get a shadow, right? So here would be what you'd expect for a shadow, which is what happened. We've actually discovered, though, that light has this ability then as a wave. Once it gets past here, remember that diagram that I showed you earlier where there was like an object here, you've got a wave front coming in, and then afterwards it's going to have the ability to move around that wave front? Well, what's basically happening here is light, I mean, yes, it keeps going here, but it had the ability to keep moving and moving and moving, and same thing right here. And it actually caused some positive interference right here in the middle, where this wave and this wave overlapped, and it actually created a bright spot right in the middle, which sounds really weird because, I mean, if you looked at a shadow of yourself, you wouldn't expect to see like a piece of light right in the middle of the shadow, but that's diffraction. Does that make sense?
Can we pass that?
I don't think I have the apparatus to pull that off. Sorry. That's where we're going from now on in physics. I'm not sure we're actually going to do any more labs. I was talking to Forrester about it, and the truth is we just don't have the apparatus to do some of this stuff. Like, we're past all of the... I used the word classical or Newtonian physics at one point with you guys, the idea of, you know, working with stuff that's like regular sized objects, you know, that are everyday life. We're now talking about things that are exceptionally small, or possibly exceptionally large and way too big for us to ever work with. So it makes it kind of tricky. So We may end up doing like an online virtual lab, but it's a lot more theory now. Wait, where was I? Does that make sense then what diffraction is? The ability for a wave to basically radiate outwards, either through or around an object. Okay. A particle wouldn't do this, but light is not just a particle, it's also a wave. You may come across this guy, Huygens, I don't know how to say his name, but he had a principle back in the 1700s, I think it was, late 1700s. He thought that waves were basically made up of an infinite number of tiny point wave sources, which spreads out on their own. It's really wordy. I thought I'd find a diagram instead. We've kind of worked with this in our Physics 20 unit. The idea of a wave front, where what we're doing is we're just going to draw circles radiating outward from something. You guys remember talking about this last year, I guess? Okay, let's see if this makes sense. Imagine that you have a wave that's going up and down and up and down and up and down, like we've learned about how waves travel, right? Well, one of the ways that we can try to represent this is what's called a wave front, where we just draw lines representing all of the peaks. Do you guys remember what we call the topmost point? The name of where it was, like the top point of a wave? Crest. Got it. Yes. Yeah. So what we do is we use like a line to represent a crest, which would be like the high point of a wave. So if you can kind of imagine a wave right here, this is the highest point of a wave. What would be happening right here? It would be the lowest point of the wave. Yeah, the trough of the wave. And then here would be the high point of the wave, low point of the wave, high point, low point, high point. Just kind of radiating outwards. Does that make sense? It's one of the ways that we try to visualize this. So that's why I like this diagram here, because I like this word propagating, like emanating from a source. This is probably the main topic for today, Young's double slit experiment. I would suggest this is probably one of the top 5 most important experiments probably done ever in science history because of some of the applications and the things we learned from it. So I want you guys to imagine that basically you're sending light in at a slide. And in the slide you cut 2 holes. If light was a particle, what would you expect? Well, you'd expect this diagram right here. Some light would hit the slide and it wouldn't do anything, right? It would just create a shadow. And some light would be able to go through the slit and it would keep going through the other side, and so you'd get a little bit of light on the screen on the other side. Here's the thing though. Light doesn't always behave as a particle. It can, but it also can behave as a wave. And what was that? Well, a wave has the ability to diffract outwards now. Right? So imagine this is kind of like the picture of this thing right here. It's actually going to go out in a wave front, creating like concentric circles as you draw that. I'm going to show you guys a lot of videos today, because sometimes that's easier than me trying to describe it. But here's what actually happens. And this, at first, made no sense. You send light through, and you'd expect to get 2 lines. You'd expect like this line and this line. And instead they got lots of lines. Like a whole spectrum of lines. Because here's what's happened. As light went through this slit right here, it radiated outwards using a wavefront. But the same thing happened right here. What is happening at this point right here where they intersect? You have the top of one wave, and you have the top of another wave. What happens when 2 waves, you have the top of both? What happens to them? It gets even larger. It magnifies it. Does that make sense? And what they discovered here is that, let's see if I can draw this. You were getting a line right here, and a line right here. And, okay, I'm not going to do this as well. You'll see this better in a video I show you in a bit. But all of these like points where they intersect, all of those are waves crashing together, like the peaks of waves coming together. And it was causing bright line spectrum across the screen. Rather than getting just 2 lines, they were actually getting a whole bunch of lines. And this was some of the first definitive proof that light was not just a particle, but it was a wave. So I think what I'll do is I'll show you guys the video, one of the first videos first. because this one, he does a pretty good job of it. And then maybe I'll come back to some of these slides. Just plug in the speakers first. Where's select? There it is.
What is light? Light from light is what is light? That's a good question. What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The color. It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right, it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today. Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes of smaller dimensions.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
You could take it out on the street.
Just taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
The obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box. Two bright bands.
Yeah, I think it'll be one line instead of two.
I can expect to see the whole box lit up.
Probably a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No,
I see dots.
How many?
it's one circle.
Oh, there's one in the middle strongest, two either side.
The two on the outside are multicolored. The one in the middle is just white.
Kind of a rainbow.
The rainbow of colour as well.
Quite a few colours, but lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah,
You'd
definitely.
expect to see two
Isn't that
lines.
amazing?
Yeah, that's incredible.
Lines.
And that's just nothing else apart from
Two slits.
two slits.
He's like flustered. He can't even put his hat on.
That's
Right?
incredible.
Well, all we're doing is we're putting light through two very narrow slits side by side. How does this make any sense?
There's some kind of principle involved there. The average person's not familiar with. That's the only explanation.
I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources.
Okay, I need to rewind that. I should have been on top of that. Okay, can you guys see?
Yeah.
This line right here,
That's what we see.
this line right there, this line right there. That's the interference pattern of these peaks hitting each other. And that's what was end up getting like shown on the far like when you put a wall over here, you're getting like a line here, a line here, a line here. Isn't that crazy?
Cool.
Yeah. I think this is the slide that I screenshotted for the actual video itself, just so you guys hopefully could see that.
This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
It's basically the same as like having 2 drops of water fall in a swimming pool. Exactly the same pattern.
As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, and then a dark spot, and a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. You saw the ones to the right were slightly colored.
Yeah, that's
because the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences, different wavelengths.
Exactly.
That's amazing.
So the difference between
So that red pen over there, and the green part, is just, I'm seeing that it's just different wavelength. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, Dave.
Thank you.
I have been enlightened.
That makes sense. Let me show you one more video and then I'll go back to my slides. This one's a lot shorter. I'll show you the next one here.
Young's double-slit experiment. Interference in light waves from two sources was first demonstrated by Thomas Young in 1801. A schematic diagram of the experimental setup is shown here. Light was made to pass through a slit, SO. The waves emerging from this slit was made to pass through two parallel slits, S1 and S2. These two slits served as a pair of coherent light sources because waves emerging from them originate from the same wave front and therefore maintain a constant phase relationship. Thomas Young observed that the light from S1 and S2 produced on the viewing screen a visible pattern of bright and dark parallel bands called fringes. What causes bright and dark fringes? A bright fringe appears if the light emerging from S1 and S2 interfere constructively, and a dark fringe appears if the light from the two slits combine destructively at any location on the screen.
So let me go back and cover some of the notes I kind of skipped here then. So from the beginning, if light was a particle, which it actually can act as a particle as well, but you'd expect that as you send light through these two slits, you just get two bands sitting right here. Right? And did I talk with you guys about how like there was this competing theory, and as long as Newton was alive, it was really hard to get anyone to believe that light wasn't a particle, because like Newton believed it was a particle, and he was just so highly regarded that no one would disagree with the guy. Right? And then he died, and then finally people were like, okay, maybe this light is actually a wave. So they started experimenting, and that's why I said this is one of the most important experiments ever. Because of some of the implications that we were able to discover definitively, yes, light can behave as a wave, Because why in the world would light go through two things like this and give you a whole spectrum of colors sitting right here? So I've got a bunch of diagrams that will hopefully help just reinforce the point. As light goes through these two holes right here, wherever these wave fronts where they cross, that was supposed to create like a light spot. Whereas like these gaps right here would be destructive interference. And so then you'd have like a dark spot. So you get like bright, dark, bright, dark, bright, dark. Obviously you get like more intense in the middle just because the light's a little bit closer. It has less time to it has to travel less distance than it does over here. You actually get like an extra, like a one less wavelength. You can do this way here. Does that make sense? I just put some more pictures here just to kind of help illustrate some of those sub-concepts. The idea of like, well, like the guy when he was tapping those two balls in the water. It's the same sort of thing. It's going to propagate out in a wave such that there's going to be like rises together, but also troughs together, but also like when one meets the other one, it'll cancel. I have a slide for that. Here it is. If they're in phase, then what ends up happening is the waves double and they get twice as deep and twice as tall. Does that make sense? And so therefore, if they're in phase and they're constructively interfering with each other, then this is where you get the bright spot on the wall. Whereas if this one's like this and this one's like this, they cancel each other out. You get a black spot on the wall. You don't see anything at all. Does that work? Okay. I found this slide just because I wanted to make it a talking point. Well, what's happening in this diagram here? Ideally, your computer should be communicating with your router. Right? But why might you get lack of service? Well, I mean, let's say you've got your cordless phones or your cell phones or the microwave, right? What's happening here is those are all radiating out electromagnetic waves as well, right? And I showed you guys one video the very first day of like, they were showing like a person sitting in his living room and these waves are coming and bouncing off of him. Like, it's pretty crazy how many electromagnetic waves are probably going through this room right at this minute, right? Like, it's quite a few now. You're going to have radio waves, microwaves, cell phone signals, you know, our Wi-Fi signal, let alone all the light waves that we have going through here. Hopefully not too many X-rays or gamma rays at least, but you know what I mean? Like, there's a lot. So, I mean, whenever you have interference, that's why, is that at some point here, you're going to be breaking this wave up and causing interference so it doesn't work anymore. Make sense? More pictures. Let me show you the other video. You guys ever heard of Khan Academy? Anyone ever heard of them? They do, it's a guy who basically makes YouTube videos kind of like I do. Basically it used to be free. I think you might have to pay for it now, but a service where he makes like learning videos about 10 minutes each on pretty much every topic you can imagine so that kids in school could then watch them. And yeah, you guys might have seen some of the videos in calculus for sure. I watched this one here and I thought the person did a good job of explaining it, so I figured, well, I've tried explaining it, let's have someone else take a crack at it too. So we'll watch this. It's about 10 minutes long.
Young's double-slit experiment looked a little something like this. You've got a barrier with two holes in it, but these holes are so small and so close together we characterize them as slits, and double because there's two of them. Young was the English physicist who first did an experiment of this kind, and what we do nowadays is we take a laser, we shine this laser at the double slit. Now the laser has to be wide enough that it hits both holes. You might think, oh my god, you need a big laser. No, you make these holes very close together. That's why you make them really close together, or at least one reason. The other reason is the distance between these holes has to be comparable. It doesn't have to be the same size or smaller, but it has to be around. It can't be a trillion times bigger than the wavelength of this laser light you're sending in here. It's got to be around the same size, or what we're going to talk about here, you won't see. You won't see the interesting pattern that's going to emerge. You might wonder what I've drawn here. What is this? This isn't a wave. That's not, this is a wave right here. I thought these were a wave. What are we doing now? Why we got this different representation? And the reason is, when I draw this pretty much just lets me show a wave in one dimension. But that's not good enough. This process is going to be fundamentally two-dimensional. This wave's going to spread out in 2 dimensions. So I can't draw it like this, I have to draw it like this. Now this whole line here, what does this represent? This represents a peak. Everywhere along here is a peak of the wave. So you've got this wave filling up this entire region. These lines represent lines where every point along there is a peak of the wave. What's in the middle? Yep, in the middle would be the trough of the wave, or the valley. So that's what I'm going to use. I'm going to use this representation for the wave. This will let me show this wave spreading out in 2 dimensions better than this one could. I couldn't draw it very well with this one. So, what happens? This wave comes in here, this laser light comes in here. Well, that part hits that barrier, it doesn't get through. This part hits that barrier, it doesn't get through. This part hits the barrier, it doesn't get through. The only portion that's going to get through is basically this portion here and this portion here. These are going to be the ones that make it through. And so what happened? What do you see on the wall over here? If this was a screen that you could project light on, what would you see? Naively, what I would have thought would have been like, okay, shoot, light comes through here, bright spot. Light comes through here, bright spot. You just get 2 bright spots, right? Well, no, that's not what you get. That's why this experiment is interesting. So you don't just get 2 bright spots. You get a pattern over here because waves don't just travel straight through this hole. When a wave encounters a hole or a corner, it spreads out, and that spreading out we call diffraction. So you're going to get a wave spreading out from down here, since it's not going to go in a straight line, it spreads out in 2 dimensions. So I had to use this wave drawing representation. It's going to spread out from the top one too. Uh-oh, look what's going to happen. You're going to have 2 waves overlapping. These 2 waves are going to start overlapping, and where they overlap constructively, you get a bright spot. Where they overlap destructively, you get a dark spot. Where it's sort of half constructive, half destructive, you might get a mediumly bright spot. How do we figure out what's going to be? Well, I can't draw this precise enough to show you that. So let me get rid of all of this mess real quick. Get rid of that. Out of the bottom hole, what would you get? You'd get this. A nice spherical pattern coming out of here. Now, it might not exactly be the same intensity throughout here, but I can't draw it with the exact right intensity. Up here, this intensity of this portion would be smaller than this portion here. The degree to which it's spreading, because this will help me visualize it. You've got this wave spreading out of the bottom hole. You also have a wave spreading out of the top hole. And now these are going to overlap. Let's draw them both. Boom. Waves overlapping in the same region. You're going to have constructive and destructive interference. And if you look, remember these lines represent peaks. So every time a peak lines up right over a peak, or in the middle, a valley over a valley, every time the wave is exactly in phase, when it gets to the same point, these are all constructive points. So right in the middle, you'd get a big bright spot. That's kind of weird. Right in between these holes, it'd be a big bright spot. Where else? Well, look at this. Right? This is constructive, constructive, all constructive. They form a line. They get these lines of constructive interference. Same with this line, constructive, constructive, all the way over to here. So on the wall, you can see multiple bright spots down here. These are all constructive because peaks are lining up perfectly. And I get another one here. You keep getting these bright spots on the wall. They wouldn't last forever. I mean, at some point it'd start to die off. It'd be hard to see. But you'd be getting these bright spots continuing on. At some point they're so dim you can't see them. And in the middle, well, wherever, let's see, what's a good point to look at? Wherever a peak lines up with a valley, so this wave's a peak right here. But for the other wave, look at, we're in between the 2 green lines. So at that point you have destructive because the peak is matching up with the valley. And this would be destructive, and this would be destructive. So in between here, you get a destructive point. The same is true. In between each of these perfectly constructive points, you get a perfectly destructive point. In between those, it'd be kind of half constructive, half destructive. It'd merge into each other. And what you get, sometimes physicists draw a little graph to represent this. You get a bright spot in the middle. This is sort of representing a graph of the intensity, 0, and then another bright spot. And it goes down to 0 again, another bright spot. They get weaker and weaker as you go out. At some point it's hard to see. Same on this side, 0, bright spot, 0, bright spot. This is the classic double slit pattern you'll see on the wall, and it's caused by wave interference in 2 dimensions. And what's the rule for wave interference in 2 dimensions? This is the same rule as the wave interference for 1 dimension. It was this. Remember, for 1 dimension, delta x, the path length difference, had to be 0. Lambda, 2 lambda, 3 lambda, so on, would give us constructive interference. And now if you're paying close attention, you might say, hold on, there was a condition. Remember, this was only true. We had to make sure.
Anybody want to grab some? we kind of do talk about this, but not in exactly the same terms here. So we did talk about like different wavelengths. Basically, like that would be the difference between here and here and here and here and here. Each of these are one further wavelength away because it takes an extra wavelength for the thing to get here. For example, like the shortest distance would be to here, and then this thing has to go another wavelength to get to here, 2 more wavelengths to get to here, 3 more to get to here. The guy will show you
That
the video
these
though.
two sources were in phase to start off with. Is that true of these light waves? It is. In fact, that's why we do it double slit like this. That's why we take one wave, we let one wave come through here. That wave, we break it up into 2 pieces. Why? Because we know if a peak was going into the top hole, well, the same wave was going into the bottom hole. That's also a peak. This is a tricky way, a quick, easy way to make sure your 2 sources coming out of these 2 holes are exactly in phase. You don't have to worry about any phase difference caused by the source. You just have to worry about a phase difference caused by the fact that these waves are going to travel different distances to different points. And what do I mean by this? What does path length difference mean here? Well, if I look at from this top line, or this top hole, this is basically like our speaker. One source here, but it's light instead of sound waves. From here to the center bright spot, the wave from the top hole had to travel a certain distance. And from the bottom hole to that spot, the wave had to travel a certain distance. So basically this we can call x1, this length x2. And the path length difference would be x1 minus x2. The difference in these, and you can just make it the absolute value if you want, but the size of the difference between these 2 path lengths. What is that going to be? For right in the center, well, that one's just delta x equals 0, because the waves are traveling the same distance to get to that point. And that makes sense. That's a constructive point, because 0 gives you a constructive point when the path length difference is 0. How about the next point? Well, the wave from the bottom has to travel this far. The wave from the top hole has to travel this far. This time they're not traveling the same distance. The wave from the bottom hole is traveling...
I want to pause before he says it. Okay, so do you guys see how the pink ones, the waves are traveling probably the same amount? Does that make sense what they're in phase? But then if you're talking about this bright spot right here, this wave had to travel a certain amount of distance. This wave had to travel a certain amount of different... Well, one of them is traveling further than the other one, right? So the question would be, well, how much further is one traveling than the other? Anyone have any idea how much further it's traveling? Yeah, a wavelength, right? Which has been defined as how far it is from here to here. So I'll let him keep going.
Farther. How much farther? Well, it's got to be the next one. It's got to be lambda. So this wave is going to be traveling, the bottom wave would travel 1 wavelength further to get to this point than the wave from the top hole, because that's the next possibility for constructive interference. Note, it's not from here to there that's 1 wavelength. This is a common misconception. This distance on the wall between constructive points is not 1 wavelength. The difference in path length that one wave travels to get there compared to the other wave is 1 wavelength. And I bet you can guess the next one. The next one, delta x, would just be 2 wavelength, and you can keep going. How about the destructive points? Shoot, you know how to do that. These are going to be the half wavelengths. Lambda over 2. This one's going to be 3 lambda over 2. And so on. And down here, what would you get? Well, if you got rid of the absolute value sign and you wanted to, you could start talking about this delta x would be negative 1 lambda. This one would be negative 2 lambda, and so on. So you could have negative values if you wanted to denote the fact that they might be lower or higher, depending on where you were in this interference pattern.
Okay, I want to just use this last diagram there to talk about a few talking points.
And
So basically, we're going to use a formula in a second here where we can actually do some math behind this. I just want to make sure everyone's clear about some of the different terminology here. When we talk about a wavelength would be from here to here. Not from here to here. The guy mentioned that. The difference between these 2 points, though, is that from like this source to there and this source to there, one of those lines is bigger than the other line by a wavelength. It's almost like if I counted them out, there's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like say 11 to get from like say here to here for this guy.
On the other one, they might be like that.
Exactly. Does that make sense? So, I mean, they both constructively interfere because they cross in the right orientation, right? But that distance is different, okay? So we're actually going to have a different distance for this. We have a different variable for how far this is. We also need to know the variable about how far the slits are apart from each other as well. So that's another distance. So there's going to be a lot of different measurements that are going to be in like meters or nanometers. One will be the wavelength, which is a meter's distance. One will be the distance between the slits, which is another distance. Another will be how far apart these things are from each other. One last thing, sometimes it's referred to as like orders. So this is sometimes called like the central antinode. And then this would be like the first order bright spot, the second order bright spot. This would also be a first order and a first order bright spot. Does that make sense? Okay, so we got two new formulas we need to learn today. And they're fairly straightforward. Just depends on what information you're given. Okay. In both formulas, this is lambda, so that's a distance, it's a wavelength distance. In one of the formulas, d is the, well actually in both of them, d is the distance between the two slits. Because that's relevant. We need to know how far apart those two holes are. Okay. X is the distance from the central fringe. And that's what the guy in the previous video was showing there. Was like as you have like your spectrum being made there, X is how far away it is from the center of that one. N is the order of the fringe. So like the middle is 0, up is 1, 2, 3, or down is -1, 2, 3. We always skip the negatives though, it doesn't really matter. L is how far it is from the screen that has the holes in it to the other screen. So like if you pulled out his drawing, like you've got this one right here. This distance right here would be L, how far it is between screens. This distance right here would be D. If you had like say different spots over here from the middle, let's say this was the middle to here, that would be X.
So the middle is the fringe?
Well, like there's always going to be a white fringe right in the middle, and we'd call that like the 0. And then this one was like, say, lambda, 2 lambda. Remember when he was drawing those out there? So this would be like the first n. This one would be the second n. That makes sense. The last thing is we can also figure out like the angle at which things are coming in at. And that's in the sine theta one as well. So
you just switch that around a bit.
yeah, I mean, ultimately, like these two formulas here, it just depends on what information you have and what you're looking for. They're not hard formulas. You just need to be able to apply them. So let's try some examples. Let's say you send in some yellow light. So we know the wavelength. So I'm just going to write down what we know. We know the wavelength is 540 nanometers. And then we know how far apart the cuts are for the double slit. You guys remember what variable we used for that? D. D is the distance for for how far the slits are apart. We're going to look for the angle. There's actually one more piece of information hidden in here. It says that we need the angle required to see the second order fringe. So that means n is 2. Because it's a second order fringe. What that refers to is like, in terms of all of these lines that you'd get on the back wall here, the 0 one is the one right in the middle. So we're actually looking for the second one. We're trying to figure out what sort of angle it would be at. That makes sense? So lambda equals d sine theta over n. For the most part, just use the formula. If you care how they made the formula, your textbook has a wonderful couple of pages of trigonometry. I don't think that's relevant. For the most part, lots of formulas we can just say, yes, someone has proved this formula works, but we'll just go with it. So you're going to need lambda times n over d. That's going to equal the sine of theta, and then we'll inverse sine it. One thing though, I need all of these units to be in the same type of unit. So if my lambda was in 540 nanometers, I can't put in nanometers for one and micrometers for the other. So I might recommend do this. Your nanometers are times 10 to the minus 9 meters, I believe. N will be 2. And then a micrometer, anybody know what it is? There you go, 6 meters. And that'll equal sine of theta. Let's see how this turns out. 540 times 10 to the power minus 9 times 2. Don't forget to put the whole bottom in brackets when you divide it, right? Before I inverse sine it, I got 0.490909 for like repeating. So then just make sure you're in degrees. I got 29 degrees. In terms of sig digs, we actually get 3. This n right here is like exactly 2. Because you really can't have like a 2.5 order. Like it's either the first one, or it's the second one, or it's the third one. So in terms of sig digs, this gives me 3, this gives me 3. This doesn't really apply. So it should be 29.4 I have.
The 2 doesn't apply?
Sure, but this 2 is like, it's like a coefficient in chemistry, if that makes sense, right? Like when we're doing stoic. No, it's like exactly 2. Like 2.0. Does that make sense?
What was the units on the D?
The D would have been in micrometers, but then I converted it to meters, so it canceled.
What was like on the original side?
Oh, so the original one was nanometers and one was micrometers. Just like that fancy UM. Easy enough? Alright, here's the second one. You've got a pair of screens. Now I'll give you different information this time though. This time I'm going to tell you that the screens are 13.7 meters apart. And we're now looking for the third order fringe. So here's like the middle, here's the first, here's the second, here's the third. And we actually get to know the distance away this was. This is 2.50 centimeters. And we also get to know how far apart the little slits in the actual, these slits right here were. That makes sense. So I can draw it nicer. No, I can't draw it nicer. Right. Here, we'll do that. There. So then the holes in this diagram here are 9.60 times 10 to the minus 2 centimeters apart. So our goal now is actually to solve for wavelength. So you want to figure out what wavelength of light would we needed to have had if we were like drawing wavelengths here. What would this wavelength need to be to produce that? Does that make sense? So in terms of information, we're now using the other formula. So lambda equals xd over nl. Hang on. xd over nl. Whoa, too far. Over nl. Same thing though, we need to put everything into the same unit of measurement. So I'm going to recommend we go with meters if we can. So what's x?
X is the distance from the 2.
So it's the 2.5 centimeters. We got to put that into meters though. So what's the ending for centimeters? 10 to the minus 2? I think so. So I'd make this 2.50 times 10 to the minus 2 meters. Then the distance between the slits was also in centimeters, but it already was to the minus 2. Good, yeah, I'd say make it minus 4. So then we'll make it 9.60 times 10 to the minus 4 centimeters. We were looking for a third order fringe, and then the distance between them was 13.7. That shouldn't be in centimeters anymore, that should be meters now. In terms of this formula here, what's going to happen is one of the meters will cancel with the other. and you're going to be left with a meters left over. But we need that because what are we looking for? We're looking for a wavelength, which should be measured in some sort of meters.
You know the distance is different.
Yeah.
There's like 7 different. It's 3.
So I got 5.84 times 10 to the minus 7 meters. You guys get that? We probably wouldn't write it like that though. Probably would write it like this: 584 nanometers. It's probably the best way of writing it. Why don't you guys go take a break? Yeah. Okay, play right now. Yeah, go take 5. When you come back, I'll finish the last. Where are these things in the office? I don't know why. Okay, I've got a few slides left to finish. Then after I finish this, the next 2 days are work days. There is an assignment that I just posted you can start working on. And I also gave you guys a worksheet to practice some of these ray diagrams. Like I've been saying, you can't be expected to draw a ray diagram on the diploma because it's not written response. But like they could test you on a question where they might ask you like, is the thing upside down or far away, or you know what I mean? So I figure it's worth practicing a few of those. But let's do this last couple examples first. Okay, so double slit, 2 slits in the thing. Well, then someone had the bright idea, oh, why not 3 or 4 or 5 or many more slits inside of it? So, I mean, now when we make these things, we call them diffraction gratings. And I was researching this. They make them with diamonds, and they cut little lines, tons of them, all on, like, say, a piece of glass or something like that. And ideally what would happen is some of the light would go through unimpeded, and it would then interact with the other light as it all goes through. Okay? So often there are many slides. If you get a question on a diffraction grating, it's not really that different. They're just probably going to give you this number here. They're going to tell you how many lines there are per centimeter. So I mean, imagine a centimeter, and they've etched 1,000 lines inside there. That's all.
That's how much it was supposed to be.
Yeah. So this right here is actually helping you to find the distance between lines. Okay. Because if there is 1,000 lines in a centimeter, then it means that in 1 centimeter there are 1,000 lines. Okay. Basically that means that between each line is 1 over 1,000. Take the reciprocal, like do 1 over 1,000. That is your distance between lines. Sean.
If this is such an old experiment, why are we still doing like work that
No.
I would say like because of the implications of the fact that this helped prove that light acts as a wave, not just as a particle. I don't want to get into it yet, but this actually has some implications in terms of the quantum world, which I was going to be showing you after Easter. We've discovered, I've been saying it a lot, light has the ability to act as both a wave and a particle. Right now we're shooting light through it. There are some weird applications to this when you don't shoot light, but you shoot electrons through it, where sometimes they act as particles and go straight through and make you 2 lines, and other times they actually give you the interference pattern. And it has to do with quantum stuff that like no one in the world actually even understands yet, and they're still working on trying to figure it out. So I don't know. I guess in general though, I mean sometimes in order to figure out where we're going to go in science, we got to first figure out what's already been learned. I mean that's why we always talk in science about old scientists who had these like half-done theories that we're still trying to work with. Does that make sense? Okay, anyways, what this really tells you is the distance between lines. So we have all the rest of the information we need. We have a distance. It says it's a first order light fringe, and we know the distance away. So we have all the information we need to throw it into a formula again. So what was that formula? XD over NL. So what is X again? memorize these. X is your distance from the central fringe. So that would be 19.2 centimeters. So 19.2 times 10 to the minus 2 meters. D is the distance the slits are apart, which we now know is basically 1 over 1,000 centimeters. So times 10 to the minus 2 meters. N is the order we're looking for, which was the first. And the length is the distance between slides. So 4 meters. Does that make sense? Just this twist right here, if you get a diffraction grading, if there are 1,000 lines in a centimeter, then it means that each set of lines must be 1,000th of a centimeter apart. So you just need the reciprocal in order to figure that out. So this number here is 0.001. Still times 10 to the minus 2 though, because it was a centimeter. So I got 4.8 times 10 to the minus 7. So it's probably going to get phrased to you as 480 nanometers though. I skipped over that last time. The reason why that's 480, because this is really like 480 times 10 to the minus 9. Because if you move that decimal place over 2 more times, then you get 480. As a consequence, though, it would have to be a minus 9. And a minus 9 is a nano of something. So then 480 nanometers is, what is it, about red light, I think? No. 600, 700 is red. This is probably closer to purple. Maybe blue light. Does that work? Awesome. Okay. Last thing here. Last experiment I want you guys to know about, not so much an experiment, I guess, but the idea of polarizing light. Have you guys ever heard of this before, the idea of how to polarize light? Anybody know what something that you probably would wear when it's sunny out to help prevent too much light from getting into your eyes? Yeah, polarized sunglasses. That's where we're going to go here in a second.
You're talking about clothing. You're talking about sunscreen.
I didn't do a very good job of helping with that. Yeah. Okay. In order to prevent too much light from getting in your eyes, you probably wear sunglasses. Let me see that I can use the diagrams here first to describe what sunglasses do. I want to use this one.
Blood, can you please call 100? Kyle Blood, please call 100.
Okay. Light as a wave is going to travel in all sorts of directions. It's going to go that way, that way, that way, that way, that way. But not only that, I mean, in terms of like which orientation the wave is going to have, you could flip that around too. So I like this diagram best. The idea that this light right here could be going like kind of out of the page towards you, into the page towards you. It's going in all of these directions. Well, sunglasses basically are a filter, kind of like a diffraction grating, I guess, in a way, where it's going to let light through, but only in one orientation. If I put the filter like this, it only goes in the up and down direction. And that means that way less light gets through to your eyes, so that it's not way too bright for you to be able to see. Does that make sense? Okay. The idea of polar... Oh, we lost these guys. Shoot. Okay, so, I mean, you guys can more or less read these slides here. The idea of polarizing light helped contribute to understanding how waves, because waves could either be transverse or they could be longitudinal. And in case you guys forgot these terms from first semester, I found these diagrams again. A transverse wave is the one that goes up and down like this. A longitudinal wave is the one that comes out in pulses. Do you guys remember what longitudinal waves are similar to? Like what what sort of wave is usually done this way? Sound particularly comes in this sort of format. I didn't phrase that very well then. Light is this one though. light is transverse. We just needed a way to prove it. Like we know now that light is a wave. The question is, well, how do we know what type of wave? Is it an up and down wave? Or is it like a pulse sort of wave? Does that make sense? So in terms of knowing which one it was, hopefully this picture can help describe it. Let's say that light was a wave that was in pulses, and you put it through a slit going this way, and then a slit going this way. The light would go through no problem, wouldn't it? Because it'd be able to fit both times. But let's say light was an up and down wave. It would fit through this slit, no problem, but then you turn a slit sideways, and then would the light actually be able to make it through in the same sort of way? You can say no. And we can actually prove this using polarized lenses, which I've got a picture for here. If you have a lens going, say, up and down, but then one going sideways, light actually can't make it through that. It's not able to. I mean, it can fit through the slits like this, sure. But then when you try to make it go through there like that, then it actually won't fit anymore. And so you actually, like, you can black it out basically by having two polarizing filters, one held vertically, one held horizontally. Try it next time you've got some sunglasses. Take some sunglasses, put one direction, put one the other direction, and hopefully it should be fairly black all the way through. Light shouldn't be able to make it through. Okay. That's kind of the idea with what I've got in some of these pictures here, is it's supposed to try to reduce how much sunlight, how much glare you get into your eyes, because rather than this light going out in all directions, really you're only letting light through in one orientation, probably up and down, rather than say side to side or diagonal, you know what I mean? So that's why I like this picture here the best. Just because if light is going out in all sorts of directions, these are your sunglasses right here. It's only letting through some of the light. Therefore, it's not so bright when you're driving. You don't blind yourself. Okay. One last thought. I had this while watching the video. Light and its ability to diffract. Hi. You guys probably know this already. Imagine that we were to turn off all the lights in the room and, like, say, black out all the windows, but say like 2 or 3. Would you be able to see in the entire room still? I'd say, well, yeah, you would, right? Why is there light up there in that corner? Well, because light comes through this window, right? But it has the ability to spread out in waves and encompass the whole room. So, I mean, one window, like, I mean, yes, you get probably a nice bright spot on the other side of the room, right? Where the light comes directly through the window. But, I mean, is the sun directly sending light into our classroom from outdoors right now? Like, where is the sun even? I don't see it directly there, right? But yet, why is light coming in through these windows? I mean, yes, it could be reflecting off of things, but it has the ability to diffract and kind of go around corners. Does that make sense? Right? And so, I mean, yes, a flashlight will send light out in a focused beam in a straight line. But I mean, if I use a flashlight and point it right there, I might be able to see stuff in the corner still, because the light is going to go out. Does that make sense? Shut.
So is that kind of like why before the sun beams up, before we see the sun, we can still see light?
Sure, we can still see light, right? Because it has that ability to bend around things. I mean, the best word to use is diffract. One of the questions I'm going to have for you guys done on your assignment is I want you to tell me about the 3 properties of EMR we've talked about now. The ability to reflect and bounce off something is kind of like a particle, in a way. Refract, change its directions in different mediums. And then the third one, diffract, which really focuses on the ability for it to be hit as a wave. Normally when we've drawn things so far, like when we draw these ray diagrams, you know, where I've got like a mirror, you know, we're kind of pretending that light is coming in as a particle, right? But I mean, it also kind of comes in as a wave as well. That makes sense. Okay, let's call it there. You got 15 minutes today. The next 2 days are work days, so we're not doing anything else pretty major until after Easter. So you should be able to get most of that assignment done though if you start on it. And I'd also recommend try that worksheet on drawing ray diagrams. I mean, there's only 8 of them. So.